talking about Ohm's law and resistance. So let's get started. Ohm's law is a central concept in electrical circuits, so we'll be going over that and then we'll be discussing resistors. So basically materials, every single material that we have tend to resist the flow of electricity through them. So basically even metals have a certain resistance to them. Now, the resistance of an object is related to a number of parameters. One is the length of an object. So basically, if you have a wire, and the longer you make that wire, the higher will be the resistance of that wire. The cross-sectional area of the wire makes a big difference also. So the thicker a wire, the lower its resistance. That's why when we're trying to support higher currents, for example, electrical lines that are used to connect different outlets within a home, we will use wires of different thickness. And finally, the material also affects the resistivity. So if we look at the equation, R is given by rho times L divided by A. The longer the length, the higher the resistance. The bigger the cross-section, the lower the resistance. And rho is basically dependent on what material you use. The voltage across the resistor is directly proportional to the current flowing through that, and that is V equal to IR, which is Ohm's law. Now, the resistance is measured in ohms. Obviously, that is given by voltage divided by area, or amps, sorry. The higher the resistance, the less current will flow through an object for a given voltage. So basically, if we want the current to flow easily, then we need low resistance. And if we want the current to flow more difficult for the same voltage or a lower current to flow, then we would require a lower resistance. Moving forward, we can look at the resistivity of different materials. Here we're looking at, for example, silver, copper, aluminum, gold. So what's very interesting is that silver is actually the best conductor, but it's not actually used in electrical wires. The main reason is cost. So copper is the most commonly used item. Aluminum is the second one. So if you actually decide to, for example, do the electrical wiring for your home, you will notice that if you opt to use aluminum wires, they'll be cheaper, but they will be much thicker than the copper wires. And you have gold, carbon, and then as you move down, you move to carbon, germanium, and silicon, which are semiconductors in the sense that for certain voltages, they're actually conductors, but below certain voltages, they actually act as insulators. Then you have paper, mica, glass, and Teflon, which are basically used for insulation. So there's the concept of short circuit and open circuit. So basically when we say we're having a short circuit, that means there's zero resistance between 2 points. But that never happens in reality, but we will make that assumption in many of our circuit scenarios. And we denote a short circuit by a wire. So basically, we always assume that a wire has no resistance, which is again not true. Now, a connection with infinite resistance is called an open circuit. Again, that does not exist. We don't have a connection that has infinite resistance. And a good example of that is basically lightning. I mean, even though the clouds are way further up and the ground is quite far away, when we have enough voltage, actually, we can pass a very massive amount of current from the cloud to the ground. That's when you get lightning. So there is no scenario where we have infinite resistance, but we will assume that when we have an open circuit, we have infinite resistance. So basically, when there's no wire, we assume infinite resistance. Now, basically, Ohm's law is related to the linearity of the relationship between V and I, where R is the slope of the line. However, that's not always true, especially if you're dealing with semiconductors. So basically, when you're dealing with diodes or light bulbs, you do not actually have a linear relationship. In the case of diodes, because you have semiconductors, whereas the voltage changes, you will get different currents flowing through them because their resistivity actually changes. But in terms of light bulbs, as the metal element that is used for creating light is heated to different degrees, it actually has different resistances. So again, it changes with that heat and the voltage. So resistors always dissipate power, and the relationship between the power that is dissipated and the resistance is given by I squared R, or V squared divided by R, and that can be easily derived based on the expression we have, which is P is equal to VI, but we can replace I by V divided by R, so we'll get the expression V squared divided by R, or we can replace V by IR, which makes us arrive at the equation I squared R. So basically, the power dissipated in a resistor is a nonlinear relationship, or has a nonlinear relationship with the current and voltage. And the power dissipated in a resistor is always positive because it's dissipated power. So if we assume that something generates power, as we mentioned before, that's negative power. And when something dissipates power, it's positive power. So we'll solve more problems in class related to this.